In this lesson, we're going to go over the natural logarithm function. Now, to begin our study of the natural logarithm, we have to first of all recall this. Recall that the power rule tells us that the indefinite integral of x to the n dx is x to the n plus 1 divided by n plus 1 plus your arbitrary constant. So, for example, if we want to evaluate the antiderivative for x squared, we would simply add 1 to the exponent here, and we would get, so here we just added 1 to the 2, we get x cubed, and we divide by this number 3 in the denominator here, add our arbitrary constant, and here we have an antiderivative for x squared. If we were to differentiate this, we would recover the x squared if we were to differentiate. So that's the power rule from calculus. However, there's one problem with this power rule. You notice that if we put a negative 1 in for the n in the denominator right here, we get back 0. If the n is negative 1, we get a 0 here. Well, that's going to be a real problem because we can't divide by 0. So in other words, if the n is negative 1, this formula does not work. So in other words, the formula doesn't work if we're trying to evaluate the antiderivative of x to the negative 1 power, or the antiderivative of 1 over x dx. So we have no way of evaluating this using the power rule. So in other words, we don't have any way of finding an antiderivative for the very simple function 1 over x. So how can we find an antiderivative for this? Well, what we have to do is go back to the second fundamental theorem of calculus. So recall that the second fundamental theorem of calculus tells us this: the derivative of the function definite integral from a to x of f of t dt equals f of x. Now, you have to recall that when we apply the second fundamental theorem here, what's in the lower limit of integration here has to be a constant. So this must be a constant right here. And then we have our x right here, and that has to match with what we're differentiating right here. If they don't match, for example, if this were an x squared, then we would have to use the chain rule. So anyway, we have that the derivative of this function right here by the second fundamental theorem of calculus is just f of x. So we just replace the t in here with an x. So for example, if we differentiate, so if we evaluate the derivative of the definite integral from 0 to x of t squared dt, this is just going to be x squared. So we just replace the t with this x right here. And it is very important that this is a constant in your lower limit of integration. That has to be a constant to apply the second fundamental theorem of calculus. So what we have now is, based on this, we can define an antiderivative for 1 over x like this. If we consider the function f of x to be the definite integral from 1 to x of 1 over t dt, then this function will have the property that the derivative of this function is going to be 1 over x. So in other words, this function right here, the definite integral from 1 to x of 1 over t dt, that is an antiderivative for 1 over x. And so just take note here, this function right here, f of x equals definite integral from 1 to x, 1 over t dt, that has the property that capital F prime is 1 over x. So this is an antiderivative for 1 over x, this function. Now, there is one caveat here. When we define this, the x must be positive. And that's because 1 over t is undefined when t is equal to 0. So you see this x right here can't be negative. We can't evaluate the integral from 1 to -1 of 1 over t dt. This quantity does not exist because we're integrating from -1 to 1, and 0 is between -1 and 1. But 1 over t has a vertical asymptote. It does not exist when t is equal to 0. So this quantity will not exist here. So this function, as we have it defined here, is really only defined for x greater than 0. And this leads us to our definition now. So here's a definition. We define the function f of x equals the integral from 1 to x, 1 over t dt. For x greater than 0, we call that the natural logarithm function, and we denote it by this special notation, ln of x. So this function we denote as the ln of x. And what we want to do now is understand this function in great detail. We want to understand what its graph looks like, various properties that it has, and what it exactly represents. So that's what we're going to do now. And here's what the graph of the ln of x looks like. It looks like this. So you notice that it crosses the x-axis when x is equal to 1, and it appears to be increasing, and it also appears to have a vertical asymptote at 0. So we're going to investigate all of these behaviors in a second. Now let's take a look at graphically how we obtain this curve for the ln of x to get a little better understanding of what it really is. So consider this graphic now. So to understand the graph of the natural logarithm function, let's consider this graphic that we have here. So in this window on the left, we have the graph of f of t equals 1 over t. So that's the blue curve right here. So that blue curve is the graph of y equals 1 over t. And down here, we have a blue shaded region. Now this point right here on the x-axis, that's the number 1. And then we have an arbitrary point labeled right here, that's the value x, which is currently 1.68. And we're going to let this slide along the x-axis, and we're going to see what happens to the graph of the natural logarithm. Now for x larger than 1, the natural logarithm of x is the area of this blue shaded region. So currently, with x being 1.68, the natural log of x, or 1.68, is equal to 0.519 currently in this picture right here. So this area right here, as we have it labeled right now, is 0.519. So if we were to plot 1.68 comma 0.519 over here, we would have a point on the graph of the natural logarithm function, and that's exactly what we have right here. That point right there is 1.68, 0.519, so this is x, and this is the natural log x. Now let's see what happens when we let this value x slide to the right. We're going to plot all those points out over here, and we're going to get the graph of the natural logarithm over here. So let's do that. So now keep an eye on this value over here as we let x slide to the right. So you see, as we let x slide to the right, we're gathering more and more area, and so our natural logarithm is increasing. So currently x is 5.44. The natural log of x is 1.69. That represents the area of the blue shaded region down here. And right there's a point on the natural graph of the natural logarithm. So you see, as we let x go from 1 towards infinity, we are recovering this portion of the graph of the natural logarithm. Also notice that the natural logarithm of 1 is equal to 0. That's because the area, if I let x be 1 over here, you'll see that the area is 0, right? So you see the area is getting smaller and smaller, and so basically right about there, the area of that, there's a little straight line segment right there. The area of that straight line segment is basically 0. And we're right there on the graph of the natural log function. So that's an important thing to note, that natural log of 1 is 0. Now what happens as we let x slide towards 0 on the x-axis? Let's see what happens there. Well, if we do that, so currently right here you see we have x being 0.38, and now the area, well, we have the area labeled as negative 0.968. Why do we have it labeled as a negative? Well, if you look back here at the definition for the natural logarithm, so currently the natural log of 0.38, well, that's the definite integral from 1 to 0.38 of 1 over t dt. But you notice that we currently have the smaller number in the upper limit of integration and the larger number in the lower limit of integration. So if we want this to actually represent the area of this red shaded region, we would have to flip these two numbers. Now when we flip these two numbers, recall, we're going to get a negative being introduced. So when we flip these two numbers, we're going to get this. And now you see this piece right here is the actual area of the red shaded region over here. So this that I have circled in red here is 0.968. But you see, by flipping the limits of integration, we now have this negative introduced in front here. And so you see we have the natural log of 0.38 is actually negative 0.968. So that's why if you look over here now, you see the graph of the natural logarithm has dipped below the x-axis. So it's become negative. So we have the natural log of 0.38 being negative 0.968. And that has to do with the way the limits of integration are ordered when x is between 0 and 1. So now if I let x go a little closer towards 0, let's see what happens to the graph of our natural logarithm over here. Well, you see, as I let x get very close to 0, you see how the graph of the natural logarithm dips downward toward negative infinity. And it does in fact go all the way down to negative infinity, and that's something that we'll have to justify later. And if you look over here, the question might be, if we let x go towards positive infinity, does this graph continue to go upward, or does it flatten out? Does it never go above some limiting value? Well, it does actually continue to go upward towards positive infinity, and that's something that we'll have to prove later also. And so this is the graph of our natural logarithm function right here. Notice that it has this increasing behavior. It looks like it's increasing. It is increasing. It is concave downward. It has a vertical asymptote at x equaling 0. It dips down towards negative infinity as x approaches 0 from the right, and as x approaches positive infinity, it does increase towards positive infinity. And so that gives us a good understanding of the graph of our natural logarithm function. Now going back to our definition, we see that this is the graph of our natural logarithm function. And once again, notice that it does go up towards positive infinity as x goes to positive infinity. Now that's something that we're going to have to prove in a second. So this does continue upward It doesn't flatten out. It doesn't do this. And it does go all the way down to negative infinity as x approaches 0 from the right-hand side. And that's something that we're also going to have to prove. And also notice that your natural logarithm function is only defined for x positive. Now let's take a look at a few properties of this natural logarithm function. So we're going to consider some constants here, a and b greater than 0, and n. So these are any real numbers. Then we have the following properties. The natural log of 1 is equal to 0. The natural log of a times b, we can break that up as the natural log of a plus the natural log of b. The natural log of a to the nth power, we can actually drop this n down in front and write it as n times the natural log of a. And the natural log of a divided by b is the natural log of a minus the natural log of b. So these are all important properties for the natural logarithm function. And let's take a look at a proof of a few of these. So number 1 is actually pretty easy. The natural log of 1 is defined to be the integral from 1 to 1 of 1 over t dt. So that's actually the area underneath the graph of 1 over t from 1 to 1. Well, the area underneath a straight line, that's basically going to be a straight line, is equal to 0. And you could actually see that if you recall the graph of the natural logarithm. Remember how it crossed the x-axis at x equaling 1. Now let's consider this one. Let's prove this. The natural log of a times b is the natural log of a plus the natural log of b. So what we're going to do is we're going to consider this function. We're going to consider the natural log of a times x. So we're going to replace the b right here with an x. And now let's take the derivative of this function. So just moving over here to give myself a little more room, if we consider this quantity, so let's differentiate this function. Now what we have to do is we have to apply the chain rule here. So what's in here is going to be a u. So we're going to differentiate this with respect to u. And then we have to multiply by du dx. Now this piece right here is going to be 1 over u. That's because the derivative of the ln of u is 1 over u. That's how it was constructed. And what we have here is the derivative of a times x with respect to x. Remember, the u is equal to a times x. This is just going to be a right here. And we end up with and you see, canceling these a's here, we get 1 over x. So what we've determined now is that this function, the ln of a times x, is an antiderivative for 1 over x. However, we also know that just the ln of x is an antiderivative for this. And so what we have then is that we have that this must hold. Just to say that in a slightly different way, what we've shown here is that the derivative of both of these functions is equal to 1 over x. So we have the derivative of these two functions being equal to each other. So these two functions, ln ax and ln x, must be equal to each other up to a constant c. Now what is that constant c? All right, well, let's put 1 in for x. So if we let x equal 1, we then get that however, the ln of 1 is 0. See, when I put 1 in here for x, I get the ln of 1, but I know that that's equal to 0 from part 1 of our theorem here. And so what we get then is that the c is equal to the ln of a. And so what we've obtained now is this result. So we've now obtained the fact that the ln of a times x equals the ln x plus the ln of a. And now all we have to do is simply think of the x as being a b, and we have our result over here. Now part 3 here is proven in a very similar manner to the way we proved part 2. So what we would consider to prove part 3, we have that written down here, we would consider the derivative of the ln of x to the nth power. So we replace the a with the variable x. And I'm not going to go through all the details like I did over here, but you'll be able to show that this is equal to the derivative and then once you have this statement, you can conclude that. And then you can reason by putting 1 in for x that the c is actually equal to 0. And then you'll obtain this result right here. Now the proof of part 4 is pretty easy. Once we have 1, 2, and 3, the proof of part 4 goes like this. If we consider the ln of a over b, well, we can just rewrite that as, so I just rewrote the fraction as a times b to the negative 1 power, and then we can invoke part 2 and say that this is equal to and then we can just drop this negative 1 down in front of the ln by property number 3. And we get that result right there. So that proves number 4. So let's take a look at this example now. So let's expand the natural log of x cubed divided by the square root of x squared plus 1. So if we consider this, so we want to simplify this quantity using these properties. Now that 1 right there shouldn't be in the exponent, that should be dropped down. So just consider what I have written here. Let's expand this and simplify it. So first of all, using property number 4, we can write this as so notice how we broke it up as x cubed, the natural log of x cubed minus the natural log of the square root of x squared plus 1. Now I wrote the square root as x squared plus 1 to the positive to the 1/2 power so that we can invoke property number 3. And now we can write this as, now notice for the first term we can drop that 3 down front, and we can also at the same time drop that 1/2 down in front. And that's by property number 3. And so we can write this as and we have our answer. And that's as far as we can simplify it. Now be careful. Don't be tempted to split this up. You cannot split this up as the natural log of x plus the natural log of 1. It doesn't work that way. Notice we do not have a property over here that allows us to break up the natural log of a plus b. We only have the property that allows us to break up the natural log of a times b. That's property number 2 right here. So don't be tempted to break this up. And that's as far as we can simplify our expression. And this comes in very handy because instead of dealing with a complicated function that looks like this, notice we have it written in much simpler terms down here involving just the natural log of x and the natural log of x squared plus 1 instead of the natural log of x cubed over the square root of x squared plus 1. This is much more complicated to deal with when we eventually differentiate functions like this. Now in order to continue our discussion and understanding of the natural logarithm function, we need to understand what a one-to-one function is in detail. So let's consider this definition. So here we have the definition for a one-to-one function. So a function is said to be one-to-one if f of a equaling f of b implies that the a must equal b. Now that's a little hard to understand maybe intuitively if you've seen it for the first time. Graphically what it means is this. If you take your function f of x, if you take the graph of your function, any horizontal line drawn only intersects the graph at most one point. So we say that the graph passes the horizontal line test. For example, down here we have the graph of the function 2x plus 3. Now you notice that right here's the graph, so the blue curve is the graph of 2x plus 3. And you can see that pretty easily that any horizontal line that we draw, no matter where we draw that horizontal line, it only crosses the graph at one point. So that means that this function is going to be one-to-one. Now let's also prove that analytically, like using this f of a equaling f of b definition up here. Well, if I assume that f of a equals f of b for this function, we need to reason that the a and b have to actually be the exact same number. Well, f of a, using this function here, f of a is going to be 2a plus 3, and f of b is going to be 2b plus 3. And now we must reason that the value a equals b. So this implies this, which then implies that now we can cancel the 3's obviously, at 2a equals 2b. And this, of course, implies that canceling the 2's now, the a must equal b. So we've now shown that if f of a equals f of b, then the a must equal b. They must be the same number. And so this is a one-to-one function. Now let's take a look at this example. Let's show analytically and graphically that the function f of x equals x squared is not one-to-one. Well, if we look at the graph of y equals x squared, that's the blue graph right here, we see that this function does not satisfy the horizontal line test. You see, if we draw a horizontal line, it does cross the graph at two locations. Now, analytically, notice this. So we want to show that f of a equaling f of b does not imply that the a must equal b. So that's what we have to show. Well, very simply, if we consider f of negative 2, that's equal to 4, of course, right? If I put negative 2 in here for x, I get back 4. And if we look at f of 2, that's equal to 4 as well. Therefore, we have that f of negative 2 equals f of positive 2. But obviously, negative 2 does not equal positive 2. So the a doesn't have to equal the b. And so that shows analytically that this function is not one-to-one. In other words, what we have here is, graphically speaking, that's exactly the way we have it drawn here. If you drop down here to the x-axis, that is 2 right there on the x-axis. And over here, if you drop down over here, that is negative 2. And so you see f of negative 2 and f of 2 are both equal to 4. And we also see that the graph of the function does not pass the horizontal line test. So this function is not going to be one-to-one. Now let's take a look at this theorem. This theorem details some properties of the natural logarithm that we've already taken note of. So first of all, the domain of the natural log is 0 to infinity. Now, that's actually part of the definition of the natural logarithm. That's not actually something we need to prove. Second, the natural logarithm is a continuous, increasing, and one-to-one function on its domain. Now that's easy to see if you look at the graph of the natural logarithm. Notice the graph here does not have any breaks in it, so it does appear to be continuous. It is certainly increasing on its domain as x varies from 0 to positive infinity. It does appear that it is increasing. And it is one-to-one. Any horizontal line that we draw only crosses the graph at one location. So it does certainly appear to be continuous, increasing, and one-to-one. Notice also that it does appear to be concave down. Its graph does certainly appear to be concave down. The limit as x goes to infinity of the natural logarithm is infinity. What that means is that this graph, if we were to continue it, it does actually continue to go upward towards positive infinity. It does not flatten out and never go above some bounding line. That doesn't happen. It does continue up towards positive infinity. And number 5 here, as x approaches 0 from the right, the natural logarithm approaches negative infinity. So you can see that from the graph here. As we let x, if we pick a point here, x, and we let it slide towards 0 from the right, you see how the graph of the natural logarithm, it does appear like it's going down. And it does, in fact, go all the way down to negative infinity. And then because of 4 and 5, the range of the natural logarithm is negative infinity to positive infinity. If I pick any point on the y-axis, there is a point x that gets mapped to it. So in other words, there is some point x on the x-axis where the ln of x equals y. And this y can be any point along the y-axis. So the range of the natural logarithm is negative infinity to positive infinity. Now let's take a look at a proof of a few of these. Let's take a look at the proof of number 2 first. So to show that the natural logarithm is continuous on its domain, what we're going to do is we're going to show that it's differentiable. Remember, if a function is differentiable, if its derivative exists, then it must be continuous. That's actually a theorem from Calculus 1. So if we consider the derivative of the ln, you notice that that's equal to, and this does exist for x between 0 and infinity. So this exists. And so therefore the ln x must be continuous because this derivative exists. Alright, so that proves continuity. Now let's prove that it is an increasing function. Well, that's actually proven by this, what we have written here as well, because you notice the derivative is 1 over x, and it's always positive for x between 0 and infinity. So therefore our derivative is positive, and so our function must be increasing. And that's also by results from Calculus 1. So since the derivative is positive for x between 0 and infinity, that implies that the natural logarithm is an increasing function. Now to show that it's a one-to-one on its domain, we're not going to go over that in detail right now. You can certainly see that easily from the graph of this function. Any horizontal line only crosses the graph at one location. Let's take a look at number 3. Let's prove that the graph of the ln function is concave down. So to do that, recalling our results from Calc 1, all we have to do is take the second derivative and show that it is negative. Well, if we take the second derivative of our natural logarithm function, so the second derivative of the ln is going to be the derivative, the first derivative of 1 over x here. And thinking of 1 over x as being x to the negative 1, you just drop the negative 1 down, subtract 1 from the exponent here, and we get negative 1 over x squared, which is certainly negative for all x between 0 and infinity. And so therefore, the graph of our natural logarithm function is concave down. And so that proves part 3. Now let's take a look at the proof of part 4. So we want to prove that as x goes to positive infinity, the natural logarithm goes to positive infinity. So we want to prove that this continues upward. Now it's going to be a little bit tricky. So what we're going to do here is we're going to consider this quantity. So let's consider the natural logarithm of 2 to the nth power. Now notice that we can write this as, we can just drop that exponent down, that's by properties of the natural logarithm. And we obtain this right here. Now I claim that the natural log of 2 is larger than 1/2. Alright, now why is that true? Why is the natural log of 2 larger than 1/2? Well, if we consider the graph of 1 over t, so say right here we have the graph of, remember that the ln of 2 is just going to be the integral from 1 to 2 of 1 over t dt. So suppose that we have, let's say we have 1 right here and 2 right here on the x-axis. So the natural logarithm of 2, the natural log of 2 is going to be this area in here. So it's going to be this area. Now, if we look at the area of this rectangle right here, draw this little rectangle right here, well, you notice the height of this rectangle is 1/2, because if I put 2 in for t right here, I get 1/2. So that distance right there is 1/2, and the width of the rectangle is 1. So the area of, say, this rectangle right here is going to be 1/2. So that area right there, and as you can clearly see from this picture, the natural logarithm, which is supposed to be the area under the curve, 1 over t, is certainly bigger than the area of this red rectangle that we have drawn here. And so clearly the natural log of 1/2, or the natural log of 2, is bigger than 1/2. So you can see that from this graphic. Alright, so now let's take this quantity and note something else. So now, because of this result, what we have is that so you see we just replaced the natural log of 2 here with 1/2. So we know that since this quantity is equal to n times the natural log of 2, and the natural log of 2 is bigger than 1/2, we know that the natural log of 2 to the nth power is bigger than n over 2. And since since the limit as n goes to infinity of n over 2 is infinity, of course, we have that the limit as n goes to infinity of the natural log of 2 to the nth power must be infinity. And since 2 to the n goes to infinity itself, since this quantity right here so what's inside the parenthesis here goes to infinity as n goes to infinity, we can then conclude that the limit as x goes to infinity of like that. So once again, we have that the limit as n goes to infinity of the natural log of 2 to the n is infinity. And we know that 2 to the nth power goes to infinity as n goes to infinity. Therefore, just replacing the 2 to the n with an x, we have that the limit as x goes to infinity of the natural log of x must be infinity as well. And that concludes the proof of part 4. Now the proof of part 5 is very similar. Let me just outline what you would do there. So for the proof of part 5, you would consider this function. So instead of considering 2 to the positive n, we consider 2 to the negative n. And we notice that this is equal to, alright, now, the natural log of 2 is definitely bigger than a half, right? So recall that the ln of 2 is bigger than 1/2. So if I multiply both sides by a negative n, that will flip this inequality. So this will imply that negative n, like that. Notice how I had to flip the inequality when I multiplied both sides by negative n. So this quantity right here is definitely less than negative n over 2. And so therefore, the limit, if we consider the limit as n goes to infinity of the natural log of 2 to the negative n, well, this quantity is less than negative n over 2, and as n goes to infinity, this quantity is approaching negative infinity. So this value is less than negative n over 2, and this is going to negative infinity, so therefore this limit must be negative infinity. Now take note that 2 to the negative n is 1 over 2 to the n, and as n goes to infinity, this piece right here is approaching positive infinity. So 1 over a number approaching positive infinity, this piece is going to be approaching 0 from the right as n approaches infinity, right? So therefore what we have is, as if looking back up here, as n approaches positive infinity, this quantity is approaching negative infinity, but what's inside here, the 2 to the negative n, that's actually approaching 0 from the right. So therefore, if we just replace this with an x, and we let x approach 0 from the right, that limit must be negative infinity. So what we've reasoned then is that the limit as x approaches 0 from the right of the ln of x must be negative infinity because of what we have right up here. And that is a quick summary of the proof of number 5. Now number 6 is a direct result of 4 and 5 and the fact that the natural logarithm is a continuous function. So this you see as x approaches positive infinity, the natural log is approaching infinity, As x approaches 0 from the right, the natural log is approaching negative infinity. So if I pick any value y on the y-axis, certainly if I go over, I am going to have to hit the graph of the natural logarithm somewhere. And so therefore there is going to be an x value in which the ln of x equals that particular number y that I picked on the y-axis. And once again, that is because of 4 and 5 and the fact that the natural logarithm is continuous. And so that concludes our proof of some of these properties of the natural logarithm function. And these properties are important to take note of because we will use them later on.